The current consensus in data engineering is that the centralized physical enterprise data warehouse is a relic. The industry standard has shifted toward infinitely scalable multi-cloud lakehouses, leaving monolithic on-premise hardware behind. Yet SAP Business Warehouse presents a contradiction. Over the past 28 years, SAP has dismantled and rebuilt its own physical compute and storage architectures 5 separate times. Despite this continuous cycle of destruction, the system remains the core intelligence engine for the world's largest enterprises. This survival is rooted in what SAP chose to keep. While the disk drives, database engines, and physical staging layers were repeatedly replaced to eliminate processing latency, the underlying intellectual property, the semantic business logic, survived. SAP BW represents a 28-year blueprint for abstracting enterprise business rules away from rigid hardware constraints, creating the logical foundation required for autonomous AI. To understand why this abstraction was necessary, we have to look back to the late 1990s. At the time, highly normalized transactional SAP R3 databases were executing core business operations and executive analytics simultaneously, relying on the exact same hardware. This created an immediate OLTP paradox. Executing complex, multi-table analytical joins directly against operational tables caused severe database lock escalations. A single heavy financial report could paralyze a company's ability to process sales orders or goods receipts. SAP's first solution was physical isolation. They built SAP Business Information Warehouse, or BIW, an entirely separate application server and repository designed to extract analytical queries out of the transactional processing environment. However, standard relational data warehouses relied on traditional star schemas. When engineers tried to knock deeply complex ERP dimensions into these models, it triggered unmanageable table explosions and severe relational join bottlenecks. This diagram illustrates SAP's engineering response, the extended star schema. A central fact table sits in the middle, surrounded by a ring of dimension tables, which then connect to a distinct outer ring of independent master data tables. The critical bridge in this structure is the surrogate ID, or SID. By generating a numerical surrogate ID and decoupling master data processing from the transactional dimension tables, these SIDs prevent table bloat and optimize the analytical reads. Inside this architecture, SAP introduced info objects and standard business content. This was the first true semantic layer, engineered specifically to translate opaque operational codes, like movement types and partner functions, into readable business metrics. By forcing this translation, Generation 1 established the practice of placing a logical layer between raw storage mechanics and business consumers. The business logic was now a distinct, manageable entity. By 2005, global enterprise deployments were scaling rapidly. Without strict modeling rules, unstructured development quickly led to entangled reporting models and duplicated data loads across the warehouse. SAP formalized their architectural governance with the Layered Scalable Architecture, or LSA. This required data to move through a strict sequential pipeline, landing first in a persistent staging area, moving to a write-optimized DSO, then a standard DSO, and finally into an InfoCube. Strict structural governance carried a high cost. To satisfy LSA requirements, engineers had to duplicate the exact same data across 4 to 6 physical disk layers. This exacted a heavy toll on hardware. Data pipelines suffered from crushing disk I/O limits, rigid batch loading windows, and the intensive administrative burden of maintaining physical aggregate rollups. The physics of row-based disk storage were effectively holding the enterprise semantic model hostage. Organizations could define their business logic, but physical hardware constraints prevented them from querying it in real time. Generations 3 and 4 replaced these physical limits with the SAP HANA in-memory platform. This stack demonstrates the principle of code pushdown. Instead of moving massive datasets up to the application server for processing, OLAP calculation logic detaches from the upper ABAP layer and executes directly down in the database RAM layer below. This shift collapsed the old LSA model. Physical aggregates were eliminated, and redundant staging layers were replaced by a single, dense columnar persistence node called the Advanced DSO. With the introduction of the composite provider, high-speed dynamic unions and joins occurred entirely in memory. Physical data replication was replaced by virtual calculation, dropping query latency to sub-second speeds. In-memory computing liberated the semantic model from the burden of physical data duplication, allowing business logic to exist independently of storage constraints. Between 2019 and 2024, enterprise data footprints fractured. Organizations adopted hyperscaler cloud environments like AWS, Azure, and Google Cloud to store vast amounts of non-ERP data. Attempting to force all of this external, multi-cloud data back into a single monolithic SAP boundary became architecturally unfeasible and cost-prohibitive. SAP pivoted its architecture away from centralized storage towards decentralized data enablement, launching SAP DataSphere and formalizing the Business Data Fabric. This model illustrates zero-copy federation via smart data access. A central semantic hub projects query paths outward to remote database nodes. It executes the calculations remotely and pulls the analytical results back, all without any physical data blocks moving between systems. To achieve this, SAP introduced Core Schema Notation, or CSN. The central hub uses this notation to translate raw tables in the remote nodes into categorized business dimensions and facts, mapping complex entities independently of the underlying physical database schemas. Generation 5 achieved the final separation. The semantic layer was now sovereign, capable of enforcing business logic and access controls without dictating where the data physically lived. Today, Generation 6 arrives as SAP Business Data Cloud, a fully integrated SaaS platform ecosystem engineered for generative AI and cross-platform lakehouses. This architecture relies on a dual-engine compute model. SAP HANA Cloud handles OLAP processing, while SAP Databricks executes machine learning workloads. Both operate directly on top of a shared open Delta Lake storage layer. This setup presents a question for data engineers. If hyperscaler compute is infinitely scalable, why preserve 28-year-old SAP BW logic? The barrier to enterprise AI is context. Raw transactional operational codes are highly compressed and opaque. Without deep contextual translation, they are entirely useless to large language models. SAP addresses this with the modern SAP Managed Data product. This curated asset packages historical business semantics, currency conversion rules, and process hierarchies into an AI-readable format. These data products automatically ingest custom operational fields and enforce legacy authorization logic, removing the need for custom manual ETL pipelines. The hierarchies and attribute relationships, first established as info objects in 1998, provide the structural context for large language models. By exposing these associations through standardized semantic schemas, SAP provides the knowledge graph that allows AI agents like Joule to navigate complex ERP data. This shift alters the day-to-day responsibilities of the enterprise data architect. Architects no longer manage physical staging layers, build redundant pipelines, or roll up database indexes. Their mandate is now the engineering of a unified, decentralized semantic mesh. SAP BW did not die. It shed its physical limitations, so its unbroken semantic core could become the intelligence layer driving the autonomous AI enterprise.